All right, morning guys. Hope everybody's doing well. My name's Chris Mason, and today I'm going to host 4 sessions here, the objective of which is to attempt to teach you CUDA. That's the idea for today. Yes, thank you, Paul. These slides will be recorded and put online in a video format, and you'll hear me talking on the video, but we don't actually make them available for download, because it's actually part of our training material as well. So what we've done instead is we've got printouts, and there'll be enough for everybody. But if you don't have a printout, Paul's at the back there. He's happy to hand them out. I tried to lay them out throughout at least some of the front ones here. So make sure you grab some slides. And if you need to get in contact with me, you want to fire me a CUDA question, let's chat. I got some cards up here, and my contact information is also at the back of the slide deck as well. So I realize it's probably impossible to do it, but I want to keep it as informal as I can. I do want to field questions. You guys are here. You probably want to ask me stuff. I want to tell you stories. I want to tell you stories about things that we've done, things that have worked well, things that haven't worked well with CUDA, some of the challenges we've faced as well. So there will be obviously some mechanical, technical stuff. That's why we're here. But at the same time, do ask questions. If it's addressed in a later session, there's 4 today. If I'm going to talk about it later, I'm definitely going to defer you to one of the later sessions. If you can't make that, just come chat with me in the break. Love to find out what you're doing. Love to hear about all the cool things that people are doing in the world. So, and all that thing. Oh, and Mick is saying he wants your cell phones off. It doesn't offend me so much, but I guess for corporate reasons, I guess they want them off. So be it. So that's it for housekeeping. I'll turn this thing on, and we'll go from there. All right, so a little bit of an overview of what we're going to talk about this morning in the first hour and 20 minutes. I'm probably going to chat for about 45 of the hour, maybe up to an hour, and then I want to do a demo. I might ask for a volunteer. Hint, I will ask for a volunteer if you guys want. If nobody wants to volunteer because it's the morning. I hate mornings, I understand. I'll do it. I don't care. I can write the code too. But if somebody wants to come up, we'll do that too. We'll talk a little bit about CUDA, give a bit of an overview of it, data-parallelism in general, the GPU programming model, specifically kernels. We'll talk about host and device, a little bit about the syntax, and just how threads work and how you might break down a little bit of a problem to do that. So this is the basic intro to CUDA, basically, is this hour right now. At the end, this slide's lying. There's actually 2 demos. We'll do one where we do some memory allocation on the GPU. After that, we'll write a kernel. So there'll be 2 demos at the end. And again, you can ask questions whenever. If you're at the back and I can't hear you, I might run down to do that. I'm missing hockey this week, so I'll take the exercise. Oh, I'm Canadian. You probably figured that out too. This is a marketing slide. I don't really want to talk too much about that because I'm more into the technical stuff. The marketing people thought this was important. So basically, the summary of what we do, we've been doing GPU computing for a long time. We started doing it with OpenGL way back in the day, taking graphics cards and fooling them to think they were doing actual, say, Maxwell's equations instead of rendering polygons and things like that. We're public. You can look at how poorly our stock is doing on our Canadian stock exchange. We also do, in addition to our products, we do release products for both the oil and gas and CAE space. We also do training and consulting. So we do a training session like this. It's usually not as large. We host those throughout the year at different locations, and we also do private on-site courses as well. We also do consulting too. So if you want to have us be your expert on CUDA, that's awesome too. I guess we've taught over 1,000 people. I don't know. I've taught a few myself. Actually, if I get to count all you guys, it goes up quite a bit. These are our solutions. Oil and gas, we do a lot of work with electromagnetic and professional services. So we do, again, it's beyond CUDA. It's just high-performance computing in general. We're software parallel architects, and we enjoy doing that. So, all right, enough of the marketing. That's it. I have to do that at the start of every presentation, but whatever. We'll make fun of it later in the afternoon. All right, so why do we use GPUs? What's the potential? Obviously, you guys are here, so you understand that there might be this platform as an alternative to things that Intel and AMD are doing on the CPU side that might be advantageous to do calculations on that might take a long time. So you're running a simulation and the computations take a long time. Hey, my core clocks aren't scaling anymore. Maybe there's an alternative platform, GPUs. This data is taken from, compiled from information provided to us from Nvidia and Intel as a reference point here. The idea being that in terms of gigaflops, you know, the GPU is winning and the CPU is losing. That's the message here. At least that's the, I don't want to say propaganda, but that's the idea anyway. The top line is single precision, and that may or may not be of interest to you. Possibly not if you're doing scientific computing. You'll see that this line down here is where the double precision began. We haven't always had double precision in our world. It's relatively new, but it's starting there. The reason it doesn't continue is the Kepler part here is really targeted initially at single precision. There will be something that has some nice double precision probably later as well, so that this line will continue. It's just not on this picture right now. So. Okay, so these are some raw specs. I'm not going to go through them all. I'm going to highlight a couple things that I like here that make things really, really lovely. In particular, high core count. And you'll see that even though the clock frequencies are slightly slower than the CPU, it's the high core count that actually gives you these big performance numbers. Along with, and this is the thing I'm particularly partial to, and I won't ever pat my chest again to avoid that sound, is the memory bandwidth. I'm going to go out on a limb and say most of you in this room whose problems the problems that you're working on are probably going to be memory bandwidth limited. And what I mean by that is the time that it takes you to transfer your data from memory to the CPU and process it is going to dominate versus the time it actually takes to compute it. Not all of you, but a good chunk of you, that's going to be the limiting factor. And this is really where the GPU wins. This is where we start to see the multipliers that you talk about, that you see all the marketing material come out from. You're really taking advantage of the memory bandwidth, and that's really important. We'll talk about that a lot during the optimization section later in the day as well. So yeah, really one of the coolest things about the GPU is its high memory bandwidth, as well as its massive computing power also. Probably the major limiting factor is the amount of memory that you're going to see. So CPU, I can just stack up, throw in a bunch of DIMMs and have like a massive processing system. You might have, I don't know, 64 gigs, 128 gigs, you know, you can throw in a lot. The GPU is, say, restricted to 6 gigabytes, 4 gigabytes, things like that. You can't add memory. It's physically soldered onto the board. Even if you had a soldering iron, I don't think it would work. You'd actually need to add multiple GPUs to the system to gain aggregate memory. It's probably the big drawback of the GPU, but again, you can use multi-GPU programming to solve this. We'll also talk a little bit about that today as well. Somebody put ninjas on this slide. Awesome. Okay, so they have, again, that's sort of the highlights is what I've basically said there in terms of better performance and particularly memory bandwidth. Disadvantages. Okay, fun with marketing. Architecture isn't as flexible as the CPU. It's not simply like I can just run my C or C++ program, compile it, and have it work on the GPU. I do need to actually look at CUDA or look at other programming languages or things like directives and things like that. Keeping that in mind, it's not just about writing it in those languages. It's really about understanding the architecture, and those are the messages I'm going to want to give you today as well. Like, what are the architectural features that I actually have to take advantage of to make this thing go fast? Also, you've got a PCI Express bus that's connecting the card to the CPU. It's relatively slow. What that means is you basically want to load your information to the GPU, run on the GPU, and then bring it back, as opposed to doing a lot of back and forth exchange. There are ways you can hide latencies, and I'll touch on that. I won't go into that in too much detail. But yeah, if you're communicating a lot with the card, it's not necessarily as efficient if you can just keep the calculation on the card itself. I say no ECC memory here, and I'm totally lying because, of course, Fermi, with the latest GPU, does support ECC memory. You can actually enable or disable it. ECC, in case you don't know, stands for error correcting capable or something like that. It basically means there's extra bits on the memory so that if there's a bit error, and typically it's a cosmic ray from outer space, it might sound like fantasy, but it's true, it'll actually flip the bit, and then you would get a memory bit error in the exchange from the GPU memory to the CPU. ECC will correct that. It will actually allow or determine that there was an error, fix the bit, and then you actually have correct data. CPU memory does this. There's overhead attached to it, so you do lose a little bit of a percentage of your memory bandwidth if you choose to have this enabled. So it's your call as a programmer, designer, engineer. Do you want it or not? Is it going to be mission critical for my application? And you can read all sorts of wonderful papers out there on how much of an effect there actually is by turning on or off ECC with respect to bit error rates. Okay, I'm going to get into CUDA now. We're going to talk about CUDA, introduce CUDA a little bit at a fairly high level. We start with compute capability. And what compute capability is it defines the set of features that you can be guaranteed to have on a GPU. So the very first Tesla that came out was called Compute Capability 1. And this was the Tesla C870. It had basic functionality. In 1.1, you all of a sudden got the ability to asynchronously memory transfer, meaning you could write to the card while you were continuing to do computations on the GPU. Double precision was introduced in 1.3. Fermi came out and it was 2.0, and that introduced caching into the memory. We'll talk about that this afternoon. And then Kepler, which is a 3.0, has PCIe 3. Why does this matter? It matters to me personally because we have existing legacy products out in the field, and so for us, our code actually has to query the device that's in the system to determine what feature sets are available, and it will run actually different sets of code depending on what's out there. So in a lot of cases, it's useful for backwards compatibility and things like that. If you're just working on your desktop and you have your card in there, you probably don't care so much about this because you know what card's in your desktop. But we ship to lots of people, and we don't necessarily know what hardware's in their system. So it's very useful for long-term development cycles and things like that. A little bit about the Kepler architecture, Fermi, and Tesla and things like that. So the Kepler still is the G-force variant of the Tesla that we have here. More core counts, basically, I think is one nice thing. Memory clock's a bit faster, good memory bandwidth. I think the thing we're going to start to see a lot more of is power efficiency as well. We're going to start to really see the power footprints come down. Why does this matter? Again, we've got customers in Houston who can't physically run more power into their facility. They've exhausted the amount of power there. It's great when you can replace a rack of CPUs with a single GPU. That's pretty sweet from a power and IT footprint and all the green computing initiatives and things like that. So, all right, CUDA overview. So let's talk a little bit about CUDA specifically. I'm going to define a couple terms. The first is the host. And when I talk about the host today, when I say host, I mean the computer, the CPU. It's the main code. It's where you say int main. That's the host. Code that's running on the CPU is the host. The device, when I say the device, I mean the GPU. So I mean the hardware that we're actually trying to use to make our algorithms run faster. And then there's common components. So there's things that are exclusive to the host, things that are exclusive to the device, and things that will work on both of them. And we'll see all of those today. So we'll talk a little bit about data parallelism. If you've done some multi-threading programming or even use, say, SSE vector instructions, you've probably got some idea about what data parallel computing is. And the idea behind data parallel computing is that you're going to take a set of data and you're going to perform an operation on it. For an example, in an array. You're going to have some tasks that are going to work on the same structure, with each task being responsible for a section of the data that's going to work on. And the tasks are going to perform identical operations. If you start performing different operations, the GPU, it's maybe not as ideal. But if you're performing the same operation like you're doing an addition, the GPU is awesome, and it'll do very, very well. The operations also need to be data independent, and the next slide will show that pretty well. So, for example, the statement on the left here, you've got you're doing multiplication. It's probably we can maybe even do it in our heads depending on what x and y are. The statements are independent. It won't matter. But in the statement on the right, you can see that we've used a in the second line there, which means that there's dependence. And again, this isn't as well suited potentially to the GPU architecture. Now, of course, if A and X are arrays, and you're doing that on large sets of data, then that's fine, and we'll see that as well going forward. So we've made an array to start with, A, B, and C. We're going to add. We're going to put element A0 plus B0, and we're going to store it into C0 here. I've arbitrarily divided this into two tasks. I'm going to say task 0 is responsible for the first 4. Task 1 is responsible for the last 4. And the same operation is applied here. You might say, Chris, well, yeah, can't you just do this in 8-way parallel? The GPU has a bazillion cores, and yeah, you can. But the point is you can choose what you're going to divide the tasks up into. And the key message here is that this is data parallel, because the addition of A0 and B0 putting into C0 is not dependent on the result of A4, B4, and C4. So data parallel computing on the GPUs, it maps extremely well to the GPU, the data parallel computing. You've got identical operations executed on a lot of different elements. So all these green bricks here are processing cores. They're actually doing math. And the picture that's kind of being shown here is the CPU actually spends a lot of time, or a lot of the real estate of its transistors and its chip count on cache and control and being able to handle large pipelines and things like that. But you see there isn't necessarily as many processing units, whereas the GPU actually spends its budget on being able to do computations, or a lot of computations. And that's the message being presented here. So again, intensity in math is a good thing. We like that. That means it's a candidate for the GPU. And if you're doing data parallel stuff, you've got all these green blocks to do that for you. I like this picture. If you had me in a classroom, I would probably draw on the board here just to show you what the physical GPU actually looks like. This device here is the GPU. This is the thing that you've plugged into your PCI Express slot. Oh, I'm Canadian. 30 centimeters, is that a foot? Something like that, about a foot by, say, half a foot, and it's pretty thin. Well, sorry, I shouldn't say that. It's actually an inch or two, maybe an inch thick. So it actually might take up more than one slot, depending on what your configuration looks like. That's what the device is. The DRAM that's on the device is not the same memory that's on your computer. This is that physical 4 or 6 gigabytes that's soldered onto the card. The GPU, there's a GPU chip that's actually located on it, and again, it's connected to the PCI Express bus. So again, this is just defining the host being the CPU, the device being the GPU. That's really the message that's being shown there, but that you do have to exchange across the PCI Express bus as well to make that connection. The data parallel portions that you're going to run on the GPU are called kernels. So when you write a kernel, that's the thing that's actually going to run and execute on the GPU. You write it like C. If you like C, no problems, you'll be fine writing a kernel. Only one kernel is executed at any given time. I'm lying, because Fermi actually relaxes that restriction a little bit. But for the most part, at least when we start, it's a good idea to understand that only one kernel is going to run at once. If you want to run another kernel, not a problem, but the first one's going to complete before the second one starts. And each kernel is going to be executed by many threads. And when I mean many, I don't mean like 10 or even 100. I mean thousands or potentially tens of thousands of threads you're going to want to run to get good efficiency on the GPU. And we'll talk about that this afternoon and how you choose how many threads you actually want to have solve your problem, because that's also critical for optimization as well. CUDA threads are sort of like conceptually similar to data parallel threads. So each thread is going to perform the same operation. And we'll see some code examples of that. The threads are going to execute independently, which means that you don't necessarily know when one's going to start or when one's going to finish. Now, there are ways that you can synchronize them together. Again, we'll talk about that. But for the most part, you have to treat them as if they're executing independently. So you as the designer are going to have to partition your problem accordingly so that it is data independent. CUDA threads are not CPU threads in the sense that they're extremely lightweight. There's very little to no context switching between CUDA threads, which is actually one of the big advantages of the GPU. So you don't need to back up registers like you do on the CPU or back up your pipelines. It's instantaneous switches, and we'll talk about that in the fourth part this afternoon, why the designers at Nvidia have chosen to do that and what the advantages are for that. CUDA threads must execute the same kernel, so the threads themselves are going to run through the same block of code. CUDA is designed to run thousands, even more than that, of threads. They're grouped together in units, which we call a thread block. The maximum number of threads in a thread block is 512 if you're on compute 1 or lower. This can't be lower than 1. Or 1024 if you're on compute 2. This is a hardware limit. It's not something you get to choose. This is just the maximum. If you attempt to launch a kernel with more threads than that, the kernel will not launch. The blocks of threads themselves are grouped into something called a grid. And the next image, I believe, shows a nice kind of picture of that. This is a two-dimensional block and grid. You can choose the dimensionality of the grid. So you can have a 1D, 2D, or 3D grid of blocks, which can also be 1D, 2D, or 3D. Why might you want to use a 2D or 3D block? If your structure is a 3D volume, it might make sense to index into that structure natively using three-dimensional indices, which is why it's three-dimensional. If you flattened your thing into an array, it's one-dimensional, use one-dimensional indices. So you as the programmer get to decide how you actually want the threads to access your data structure. You also get to set the dimensions at launch time. So what that means is they don't have to be known at compile time. You can change it from call to call. So you can set the amount of threads that you want your kernel to run at launch time. So let's take a look at the program flow. So we've got a program flow. So these little squiggly lines are representing the threads. You start with the host again being the computer called int main. Great, it's running. You launched a kernel. Now I chose to launch the kernel. I can't count that many. I mean, I can count that high, but that's pretty small. So let's say that's 12. So it looks like we've launched a block with 12 threads in it in a 2 or a 3 by 2 grid, and we've called this kernel. Now the kernel is going to run 6 times 12, let's say 72 threads to compute and solve this problem. Then it finishes. The host begins, and now we're going to launch another kernel here. You'll notice that there's a different number of threads, and I've changed the dimensionality of the second call that I've made. So you can change this from call to call. It happens to be a separate kernel. This is kernel 1 and this is kernel 0, but you could relaunch kernel 0 with a totally different thread and block configuration. So the host is responsible for launching the kernel. It executes serial code in between. The host is going to be responsible for memory management, including GPU memory management. It's going to be responsible for exchanging data to and from the device, and it's also responsible for error handling as well. Today, we're going to talk about the CUDA runtime API. There's sort of 3 variants that you can use to program the Nvidia GPU. I guess, again, there's more than that if you start counting directives and things like that. Today, it's the runtime API. The runtime API is a really great way to start. If this is going to be the first time you've programmed a GPU, I'd strongly recommend going through the runtime API to get yourself familiar with it. The reason being is because when I say they, I mean Nvidia has done a great job abstracting some of the really nasty details of parallel programming away from you that you would see if you used, for example, the driver API or OpenCL. The driver API and OpenCL are wonderful APIs. They're great. We use all 3 of these. But the deal is OpenCL and the driver API are a little bit lower level, and you have to do a lot more explicit initialization and creation of context and things like that. So for example, if you use the runtime API, it automatically initializes the GPU for you. That's not the case with the driver API. So it's great, again, a good way to start with the runtime API, but when you get into a very large software project, you may want to consider using the driver API. So for example, you can do, say, more queries on the system before you try to initialize the GPU. Gives you a little bit more flexibility. The driver API looks nearly identical to OpenCL as well. So all work on NVIDIA, and they all work wonderfully. Performance-wise, we've seen almost no degradation, maybe a couple percent. Sometimes OpenCL is even faster. Like it's pretty uniform across the board. NVIDIA's done a great job, again, of keeping all 3 of these APIs the same. So from a performance perspective, you're not losing anything by picking one API over the other. For learning purposes, runtime API to start. Okay, so let's talk about some of the ways we actually launch our kernel. The kernel itself, and we have some code examples coming up. But you'll launch a kernel just like you were to call a function in C. You put the name of your function, which which is my kernel, or name of the kernel in this case. You specify the grid size, then the block size, and then you pass in your function arguments as you would in C inside your curved brackets there at the end. So the only difference is they use the chevron syntax here to denote what the size of the kernel that you're going to launch is. In terms of the maximums that you can do, you might say, well, Chris, look, you mentioned that I can only have 1,024 threads. That's not very many. Right, but you can actually have a grid of 6553 blocks of 1024. So in fact, you could actually have 65535 times 65535 times 65535 times 1024 threads. I promise you'll run out of resources on the GPU before you run out of threads, okay? The other thing that's a little bit misleading about this slide is, let's say we have a three-dimensional structure and we launch it with, say, 64 by 64 by 64. Well, you'd say, okay, well, Chris, that fits under the maximum. That's great. That's going to work. That's actually a launch failure. And the reason is it's a total. So you actually have to multiply x times y times z. That total must be less than 1024. Okay? So even though the maximum is 1024, if you were to call it with a block size of 1024, you would have used up all your 1024 in the x dimension. So you could, the other two dimensions would have to be 1, or you get a launch failure. But grid size, not a problem. I'll give you a hint. We'll talk about this during debugging as well, though. Oftentimes, you'll mistakenly launch, once you get into really large problems, you'll actually probably exceed this limit. And it's kind of hard to figure out all of a sudden because your kernel didn't launch, but you don't know why. But you actually probably launched it with too many grids once you start to expand to really large data. It's easy to actually get above 1024 by 65535. The kernels themselves, so we saw how to launch a kernel. Now, how do we actually write the kernel? The kernel, again, it looks just like a C function. The only difference is you prefix it with underscore, underscore, global, underscore, underscore. This is called from the host, but it's actually executed on the device. So only the code underneath, inside the parentheses, underneath this thing will actually be executed on the device. Everything else is executed on the host. Few restrictions. You don't have access to host memory in general. There are ways around that, but at least, again, at a preliminary level, you don't have access to host memory. You have to return void, so you can't return a value. The values you're going to get back to the CPU are going to be as pointers in your argument list. They're not going to be returned as a return type. No function pointers and no recursion isn't quite true anymore because Fermi does support that. That being said, when you start to do things like that, you introduce a stack, which is actually somewhat slow, and we'll talk about that in the fourth lecture for today. You can't have static variables, so you can't have variables that retain their value from call to call. You're going to need to store those in pointers in global memory from call to call. And you don't have access to host functions, so if you wrote the world's most legendary swap function on the host and you want to use it on the GPU, you're going to have to rewrite it on the GPU. It doesn't just automatically port over. You'll need to port that to the GPU as well. This is a kernel, as promised, underscore, underscore, global. It's called simple kernel. It takes 2 pointers, A and B, sets the 0th value of A to B. This is a really bad example because if you launched 1,000 threads to do this, they would all set the same value of, all 1,000 would set the same value of A and the same value of B, which is excessively redundant. The kernels need to be declared, but not necessarily defined in the source or header file. So when you call your kernel down here, you at least need to forward declare it here. You can also obviously define it in the same function. So again, here's your prototype right there, and then you're launching it here with these sizes. Also with the sizes, oh, it's brutal. Don't mix these up. Oh my goodness, it's hard to debug because it launches oftentimes, and then you have to figure out why your thing isn't working or it isn't addressing the data properly. The grids need to be the first entry and the blocks need to be the second entry. I guess I'm a Commonwealth nation because I remember it as Great Britain, but however you want to go with it, like you need to put the grids first and the blocks second. And like I say, it's a nasty problem to debug if you mix those sizes up. The indexing gets all messed up in your kernel. So make sure that that's correct. you can you kind of initialize it. It looks like a template, sort of. So you pass in n would be the grid size here. You're launching it with 512 threads per block. This is a one-dimensional launch. If I go back a slide, this dim3, sorry I didn't elaborate on that, that's a three-dimensional, it's a very simple structure. It has an x, y, and z component to it. And so you would set grid size.x equal to 5, grid size.y equal to 10. And I think we have some code that will actually illustrate that as well. So you can either pass it in using a dim3 argument, or you can pass it in as a scalar instead of the vector type. And this just launches it one-dimensionally, but you can launch it with multiple dimensions using this dim3 structure. So n blocks of 512 each. That's what's being launched here. The kernels themselves have some built-in variables that are critical to figuring out. They're basically the GPS. Where am I in my kernel? Where am I in my data structure? And these are the values that you're given. They're built-in variables into your kernel. You don't pass them in. They're read-only. You can't write them. If you want a different value for these, you should have launched your kernel with different values. And you can. So it's pretty flexible that way, it turns out. But once you're inside your kernel, these values are read-only. You can't change them. So, for example, my thread index. This tells me what index am I in my thread block. Am I thread number 17 in block index number 5? Why is that important? Because that points me to an appropriate data structure that I'm going to work on, or appropriate part of memory that I'm going to work on. You can't vary the size of the blocks or the grids during the kernel call. I like this slide. I think this slide really does show what's happening here. I launched my kernel with 3 blocks of 5 threads each. Okay? There's my 3 blocks. They have 5 threads each. Thread index will go from 0 to 4. Let's see, we started 0. 0 to 4, 0 to 4. And my block index will go from 0 to 1 to 2, basically. This computation in the lower left-hand corner says the block index. And again, block index is a 3-dimensional structure. It has x, y, and z components. But because I'm 1D here, I'm just interested in the x component. This structure here will give me my global index. So this calculation will calculate 0 through 15. Let's check. So if I pick thread 3 in block 1 is the block index times the block dimension, which is 5. So 1 times 5 is 5. It's not that early. Plus 3 is 8. So that gives me thread index 8. This calculation here is how most of your kernels are going to start. Most of my kernels start with this calculation. Int index equals this blob here. It basically tells you what global index are you going to be working with. I stole this bullet, it looks like. Yes, that's what you're going to be doing pretty much at the start of your CUDA kernel. Another useful calculation to determine your grid size, it's in the Nvidia Programmer's Guide, and we use this one a lot too. So let's say you have 10,522 elements in your array. You know your block or your thread block size is going to be 512. How many grid elements do you need? You take the total size, so 10,522 or whatever number I said, add 512, subtract 1, do integer division by 512, and that will give you the actual number of grids that you need. If you think that you could get away with size divided by block dim, you'll realize it doesn't quite work if it's an odd number, and then you have to add 1, but that doesn't work when it's an even number. So that's what this calculation is doing for you, is it's helping you figure out the number of grids that you need. Again, max for block dimension is 512 and 1024. And then the grid size becomes the number of blocks that are in the grid there. So it's a handy calculation. I've pinned it to my cubicle wall. How about that? All right, let's take a look at some kernels. We've got some kernels. When we write these kernels, what is the output of these kernels? So we have some memory A. We have my kernel. We have these, again, we start off with our fantastic calculation. And basically, we set the value of A at the index to 7. And not a surprise, all 12 elements get set to the constant 7. Nothing exciting there. In the next one, we still do that index calculation, but instead we set the memory to block index. The first 4 are where the first block occurs, and they all get set to 0. The second 4 get set to 1, and the last 4 get set to 2. So we're setting the block index to that. And then finally, in the last kernel, we set it equal to the thread index, and we see it increase from 0 to 3 and then repeat as we go through the block. So I'm hoping this picture works perfectly in your mind with this picture. If you like those pictures, you can forget everything else I've said. That's what I care about. That I think is critical for you to understand. All C operators are supported. You can add, you can shift. That's a bit XOR. You can do all the binary operations and things like that. You can call functions from the standard math library. You can do sine and cosine and logarithms and things like that. You can also write your own device functions. So you're like, Chris, yeah, I have 10,000 lines of code. I'm not going to write a 10,000 line kernel. Awesome. That's probably good programming practice not to do that. You can actually have device functions that are actually executed on the GPU. These device functions, float my device function, it seems like it's returning a type. It's sort of inlining it, or when they build a stack, it's actually building a stack like they do in C. But otherwise, pretend that it's basically inlined. But that way, at least you're abstracting your code into different modules, and that makes it easier for testing and debugging and things like that as well. Device functions can't be called by the host, so you'll get a launch error if you attempt to do that. But they can be called from other kernels. So that way, you have a big blob of code in your kernel. You can extract the section that you want, put it as a device function, and then go from there. You can have if statements, while statements, and for statements inside your kernel. That's all good. When you do that, though, do realize that all your threads are doing that. So all your threads are going to be looping together. So that's something to think about as well. Ifs also cause branching. We talk about the performance impacts of branched code in lecture 4 today. You have some special data types. The data types that you get, you have the normal ones. You have int, you have char, you got all that stuff. But you also get vector variants of the code. This becomes a little bit more interesting when you do performance optimizations, potentially. But you can have, for example, a float 4 that contains 4 components, an x, y, I'm going to say it, z, and w component. Although I'm teaching my daughter z. I want her to, instead of z. Anyway, x, y, z, and w members that you set these values to. It's useful for memory performance reasons why you would actually use these vector types. And again, that's something we'll talk about more this afternoon. So these types are available to you. dim3, that variable that we use to launch our kernel, also has x, y, and z components as well. So these are the variants. But you can just use normal stuff too, right? You can just use float and char and things like that. All right, memory management. So instead of mallocing your array, if you want to malloc an array on the GPU, you call CUDA malloc instead. You'll give it a pointer and the size in bytes, not the size in elements, the size in bytes. You can also do a memset, and then you're going to want to do a CUDA free to release the memory at the end when you're done with it. So in this case here, my size of my array is, say, 1024. I've got the size of bytes. I've got this pointer A. Notice I take the address of this pointer to pass it into CUDA malloc. You don't necessarily need to do this explicit cast anymore. It doesn't give you a warning. You pass in the number of bytes. We're setting all the values in that array to 0. Then we free it. That's how you allocate the memory on the GPU, is by using CUDA malloc. It's critical that when you allocate your memory on the GPU, realize that it's on the GPU. It's not on the host anymore. It's just a number. It's a gross number. It's some hexadecimal number. If you try to dereference that on the host, you get a seg fault because it's not on the host. It was intended on the device. Reciprocally, if you pass in the host pointer to the GPU instead of that device pointer that you allocated, that's no good either because it doesn't have any meaning on the GPU. Now, and you can't tell from the pointer. You can't just look at it. I mean, like I say, it's just some hexadecimal value. You can't tell if that's being referred to on the host or the device. So if you choose to dereference a host pointer on the device, spectacular things start to happen. Your screen starts to flash. You'll actually, if you do real good, you can overwrite it. It looks like the Matrix. I kid you not. They start coming down the screen like that. And if you do a really good job, you'll reboot your system. It's spectacular. Now, that being said, Nvidia is doing a better job also of providing the driver protection so that it's keeping the system more and more stable. But you got to make sure that that in your kernel, you're only using pointers that you've done CUDA malloc on, okay? Not malloc. All right, how do I call? Well, you're like, okay, fine. I have my host pointer and I have my device pointers, and you told me to be very careful with them, and I'm very careful, Chris. Okay, great. How do I get them from the host to the device? You use something called CUDA memcopy. You put in your destination. Let's say we're copying from the host to the device, so this would be the device pointer. You've got something that's your host pointer here. You're going to take the size in bytes, and that's going to copy it from source to destination. That will copy it across the PCI Express bus. You don't have to worry about the mechanics of it. It just does it. The enum memcopy direction tells you basically what's the direction of travel there. There is one CUDA memcopy default as well, which can kind of deduce these now using the new Fermi architecture, but it only works on Fermi and beyond. It's probably better to document your code anyway by using one of the appropriate ones so you know which way it's actually going intentionally. This is a blocking call, meaning it's going to wait until it's finished. So it's going to, the CPU is going to sit idle until all that memory has been transferred across the PCI Express bus. And it will also wait for all outstanding CUDA calls to complete. So if there's been some CUDA calls, it will stop, and it will not copy until the CUDA call has finished. And that way you can be sure that, well, how did I know if my kernel finished or not? Well, the first thing CUDA memcopy does is it waits till the kernel finishes. That's the idea there. So that way you're guaranteed that the results are in the appropriate memory before you transfer them. That's sort of alluded to in the previous slide that kernel launches themselves are asynchronous. When I launch a kernel, it returns immediately to the CPU. It gives control right back to the CPU. And then the kernel will start executing once all existing or queued up kernel calls have completed. So again, one kernel at a time. But the CUDA memcopy itself is synchronous, so it will wait until all kernel calls. If you have 10 kernel calls queued up, it's going to wait until all 10 are complete. Then we start the copy. And again, that idea is that, okay, we wait until the kernel's complete. You can force a synchronization by calling CUDA device synchronization, which is going to block until all CUDA kernels are complete or all asynchronous calls are complete. Pretty much the first line of CUDA memcopy is CUDA device synchronize. It just waits until everything's complete before it begins. Error management. Most CUDA functions are going to return an error code to you. You probably should check them. Whatever, your call. You can get the error type, the error string. It actually is a nice string. It actually says, hey, this is what you did wrong or success. This one's nasty. Kernel launches don't have a return value, right? They're a void. Again, you have to return void there. So let's say you mistakenly launched your kernel with too many threads. That kernel isn't going to run, but it's not going to tell you it didn't run. That's the best part. So what you need to do is you need to call CUDA get last error after that kernel call. It will actually record the last error. It'll say, hey, you launched your kernel with too many threads. That's a problem, and you can call get error string to print that out. If there's multiple errors, it only records the last one. And again, for kernels, because it's asynchronous, you're going to need to call device synchronize then CUDA get last error. So that one's a little bit tricky because you launch a kernel, and then you call, okay, I'll call get last error. But it hasn't quite gotten to the card yet to fail to get back. So CUDA get last error returns success, even though it fails milliseconds after that. So you're going to want to synchronize first, then call get last error. So a little bit subtle. So again, it's because the kernel launches are asynchronous. Awesome. We have lots of time for our demos. GPUs are data parallel architectures. In CUDA, we have a heterogeneous model. There's a host. It does the memory management. Data transfers. It does the data transfers to and from the GPU. It launches the kernel with the sizes that you've chosen, and it does error management. The GPU itself, it does the heavy lifting. It executes the data parallel kernels. It's pretty much just plain old C with a few important extensions and a few restrictions as well. So, all right, we've got 2 programming demos. Yeah, we'll have plenty of time to get them done before the end here. The first one is we're going to allocate memory and transfer data to and from the GPU on my laptop, and then we'll write a simple kernel to do some vector addition. That's going to be the demo. All right. I'm sorry it's in Windows. If you prefer Linux, sorry. All right. All right. I promised I'd ask for a volunteer. Who wants to code this morning? Anybody want to code? Nobody wants to code? No? All right, come on up. Okay. Let's see. You can have the seat. I'll talk while you do this. If you guys want to offer suggestions, and sorry, your name? Kieran. I'm Chris. Nice to meet you, Kieran. Awesome. Okay. All right, so we're firing up Visual Studio. My laptop has a CUDA GPU in it, and I'll help you out just by opening this. Actually, Visual Studio is kind of nice, and since it does color coding and all this kind of stuff for you here. So yeah, I'll just walk the people through the code, and then we'll get you to enter some stuff or whatever, and go from there. So yeah, so the code here, as you can see, we've got an int main. This is all running on the host. What we've done for this exercise is we've actually put the H denotes that it's on the host, and the D denotes that it's going to be on the device. This is the size of the array that we're going to allocate. It's going to be a floating point array, single precision. We're going to malloc this information. There's this fun little function we wrote called GPU properties, which we'll look at later. We generate some test data into both A and B. It's just random garbage data. Basically, the idea is we're going to allocate this data. We're going to put that there on the GPU. We're going to mem copy it from the CPU to the GPU. We're going to take it back from the GPU into array an array B, and we're going to compare A and B basically to make sure that they're the same. So we're actually not launching a kernel here. We're just doing memory transfers to and from the GPU, and then we'll free the memory at the end here. So before we get started, yeah, my GPU is that I have here. It's Quadro NVS 4200 or something. It's actually an Optimus GPU that Dell makes, so it has like an Intel part to drive the graphics, and then it has like the actual separate Quadro part to do that, which is kind of nice for debugging, and we'll see that this afternoon. So, all right. Do you want to try typing in a CUDA malloc call? Does anybody have any suggestions? Or you can type it in if you want as well, right where my cursor is blinking there. So I'll give you a hint. It'll be CUDA malloc. Nice work. Perfect. Open the bracket. Good stuff. And now we're going to need to take the address of the device pointer. Now I'll just scroll up for a second on you here, Kieran. And we're actually going. This will be our device pointer. We've arbitrarily done that. So you want to use the ampersand symbol. Perfect. And then AD for that. There you go. And it needs to be the size in bytes. And so we've defined a nice little thing there. So you can put a comma after that guy, and yeah, put the n bytes in. Nice work. And then we'll close the bracket and put a semicolon after. Awesome. Now this does return a type E, so we should actually set this equal to E. We'll do that right here. We'll set this E equals. Yeah, E, yeah, like, yeah, the letter, yeah, perfect. E equals, awesome, nice work. Yeah, because it's going to return a type. Let's say there wasn't enough memory on the system or whatever. That'll return an error type. So we've allocated this many bytes onto the GPU. Nice. Okay, so this is looking good. All right, now we're going to want to use CUDA mem copy here. So again, E equals, because, yeah, we'll get that return type. And then it'll be, yeah, CUDA mem copy. And it'll look like this, this guy right there. Yeah, CUDA mem copy. Perfect. I think it's a lowercase c, actually. I don't like that so much. Perfect. And then we'll open the bracket. All right, now we need the destination pointer, which is going to be AD, our device pointer. And it's going to come from our host pointer, which is AH. So that'll be our source. Again, the size in bytes, so we'll need to pass the number of bytes. So n bytes again. Perfect. And then put a comma as well. Now the mem copy type, I always have to remember. So it'll look like CUDA mem copy. So you can start by typing that. And then you're going to need to write capital H host, and then capital T2, and then capital D device. Nice. And you can close the bracket and put a semicolon. Okay, so what Kieran has typed in here is he says, okay, I'm going to take my host pointer data. I'm going to copy it to my device pointer data, size of n bytes. And it's going to go from the host to the device. Now, interestingly enough, if you had put device to host here, the API reports an awesome error for you. It'll say invalid direction of memory transfer or something, or trying to put a host to device pointer. It gives you a nice error message. We can actually try that after. All right, so all we're going to do is copy it back. So if you want, you can just copy this line, because we're going to be lazy a little bit here. And we can just put it right there. And so we need to switch the order of things now. So, and we want to copy it into array BH. So the destination will be BH instead of AD. Sorry, yeah, instead of AD, it'll be BH, because we're going to copy it back to the host. Perfect. And it'll come from AD, and we need to switch the order of, yeah, exactly. We need to switch the order of CUDA memcopy there. So now we're copying it back from the device to the host. Awesome. Now, this will work. This comparison of data, we just wrote a little utility to make sure that the original A data and B data are the same. We should probably free our memory, so let's call E equals. Again, we'll just get that nice error code. And CUDA free. Perfect. And then we'll open the bracket and have AD, just the device pointer, and that's it. Okay, nice work. So the highlights here, again, when you malloc it, we have to take the address of that pointer, because you have to assign it a value that you've malloced it. We're going to memcopy it back, and free the data. All right, I'm going to build this thing now. Oh, it's write protected. That's nice. Sorry, yeah. Okay, well, let's see. I'll remove the write protection. I'd write protected the original so I wouldn't overwrite them by accident, and then forgot to remove the write protection on the working ones. Well, let's see if this works. I have no idea. All right, so we'll start without, oh man, actually overwrite. Yes, let's try this. I'm an admin. I can do this. All right, okay, so some of the highlights here. This was called by that GPU properties. I'll actually show you that section of code where I'm actually querying my GPU. So it tells me I have an NVS 4200M. I'm compute capable 2.1, and I have 512 megabytes of memory. The arrays match is a good thing. That meant our arrays matched. If we had made a mistake, it would have said arrays don't match. So, but maybe you don't believe me. We could actually insert a bad value, but it actually does that. So I'll take you through the code here. So the GPU properties here is where I'm actually querying all the properties. These are all very nicely documented in the API. So you can find out the information that you get. So I'm getting the device, and then I get the properties of the device, so I can find out its name, its compute capability, total global memory. That's one of like 20 or 30 things that you can query the GPU for. You can find out all sorts of wonderful things out about the GPU. So, well, for fun, let's try to mix up that order. Let's say we screwed up here, and we actually, let's mix this guy up. Let's say we copied it, so we can just change device to host, say, for example. So yeah, we'll just put you there. And let's say we accidentally put the wrong order. We should get a nice error, and it should also tell us that the arrays don't match anymore. So we made a mistake, and we did this. Awesome. So let's try to build this. Okay, and we'll run it. Okay. Yeah, so actually it's exited. It doesn't actually get to the comparison because we force an exit on it. But yeah, so it says invalid argument there, meaning it didn't like the device to host call. Perfect. Awesome. That's demo 1. Thanks, Kieran. Awesome. Thanks. Great. All right. Does anybody want to come up here and do demo 2? You saw how evil I was, right? It's like totally making fun of you. No, I'm kidding. But I will unwrite protect it. All right. Oops. Okay. So we're going to do a simple kernel. Anybody want to come up? Anyone want to try? Awesome. Thank you. Hey, it's in your name. Ramesh, I'm Chris. Nice to meet you, Ramesh. Awesome. All right, grab a seat, and we'll do this. Okay.
You have to get your daily dose of coding, right?
Yeah, seriously, right? Yeah, exactly. Get the code in for the day. All right. Okay, so I'll take you guys through this code again as well, and show you what you got. Again, we've got a nice generated test function, which is going to generate some random data. We're going to compare the data and check the error functions again. A bunch of host pointers. So what we've got is some host pointers. We're going to take A and B in the host pointer, add it to C, and we're going to store it in C. The ref H is just the reference result, so we're going to compare against reference H on the host. And our device pointers are A, B, and D here as well. We've also got some nice parameters for grid size and block size, although we can just put them in scalars if we were to so choose for. This stuff, by the way, is initialized all with ones as well, so it defaults to 1, 1, 1 in its X, Y, and Z components. The size is a little bit gross. We'll deal with that. It's you know, something maybe more realistic. It's not a perfect multiple of 2. It's 2053, so that's fine. Generate the data. We've actually allocated all the data like Kieran did in the last exercise here for us, and we're checking our return types and all that. And heck, we even copy it to the GPU. So the whole point here is just to write the kernel, launch it, and make sure that it all works out all right. So the only thing we're actually going to have to do here is actually add a snippet of code to launch the kernel. And it frees it all up for us all nice. And we'll also here, we'll probably insert our kernel to write there as well. So maybe let's just start by writing the kernel, if you're okay with that. So give yourself a little bit of space there, and we'll fill it in between, yeah, exactly right there. So needs to begin with an underscore global. Yep, perfect. And an underscore needs to return type void. You can call it whatever you want, maybe add kernel or something like that, whatever. Perfect. All right, and we're going to open the function argument. Perfect. And then it's a floating point, so float. You can call it star AD, for example. Yep, and then you can have another one for BD and CD. Awesome. Okay, and then, yeah, actually we don't even need to prototype it. You can delete the semicolon. We'll just fill it in right here. And so we'll start with, yeah, exactly. Of course, you could do exactly what Ramesh was doing there as well. Okay, so before we begin on this guy, yeah, I'll talk for a second so you can take a break. Thanks. One thought here, and one of the mistakes that I see a lot initially right here is people will say, okay, so I've got my device pointers here. Well, how do I add an array? I scroll from int 0 to the size, and I iterate through. So C is equal to AI plus BI. And you go through the for loop that way. Well, sort of like the matrix, there is no for loop. There is no spoon. There is no for loop anymore. There's no need for the for loop. Because remember, this code now in this section is going to be run thousands of times by the thousands of threads you've launched. There is no for loop. Okay? So because it might only look like one thing is executing, not true at all. You've got this running thousands and thousands of times. So the first thing we need to do, sorry, Ramesh, I'll just run back up here. Ooh, nearly tripped there. Yes, we need to calculate the index. Yeah, so call it whatever you want. And that's going to be equal to, and I'll help you with the syntax here. It's block, capital dim. Yeah, sorry, perfect, block, yeah. And then dim, capital D, dot x, times, and you're going to need block index, IDX, capital I, yeah, dot x, plus the thread index, IDX, capital I, dot x. Okay, sorry, dot x. Perfect, semicolon, awesome. So what this is doing is this is being launched again 1,000 times. Remember, each thread is going to have a unique value for its index because it has a unique block index and a unique thread index. That's the index that we're going to use into the array. So it actually simply becomes CD, the index, equals, yeah, A plus, yeah, A index, B index. Nice. Perfect. Nice work. So, no for loop, because this is being run, oh, really? Oh, sigh. I'll fix this in the break for you guys. Overwrite, I'm in it. Okay. Yeah, so the idea here is, you might say, well, how's this actually adding up thousands of elements? Well, we actually have launched this kernel thousands of times, and so because of that, all these threads are actually executing in parallel. So we're doing this addition in parallel. So we've removed that outer for loop. All right, now we need to launch the kernel. So we're going to go down into the main code now. Yeah, sure, go for it. We can build it. It should build. If it doesn't, we'll fix it. Oh, yeah, sure. Okay, perfect. Okay, so the arrays don't match. Now, the reason they don't match is we actually haven't launched our kernel yet. So we haven't actually called it. So we've written it, but we actually haven't called it anywhere. So let's jump down into the main code, and we'll launch it right where that comment was. Sorry, if you scroll up just a little bit there for me. Perfect. Add vector element wise right there. So we're going to call your kernel, which I can't remember what we called it, add kernel or something like that? Yeah. Perfect. Yeah, so add kernel, sorry, yep, the name of your kernel. Now we're going to need to use that, it's a triple less than sign, and then what we're going to need to put there is, yeah, the number of, exactly, the number of blocks, which in this case, we can calculate it using, and we probably won't actually maybe even want to use that, that fancy calculation here, so I can help you out with that. So just above this, if you want to put grid size.x, yeah, right under there is perfect. So grid size, yep, .x, I think that's what I called it. Yep, perfect, equals. All right, so it's going to be, now we haven't defined it yet, but, or sorry, we have. So n, it'll be capital N, yep, plus, because that's the number of elements in our array, plus the block size, so block size.x, which we haven't defined yet, we have to do that too. And then -1, and we should probably put this all in brackets, and then we're going to integer divide it by block size.x. So just, yeah, just a slash, perfect, block size.x. We need to also define block size.x. So let's do that a line above. And we'll launch it, say, with 512 threads. Perfect. So this should launch with 512 threads. Grid size should work out to be about 5, I think, because I think 2048 will get you 4 blocks, basically. So this calculation should give us 5. So now you can just pass in grid size and block size. Yep, inside that. Awesome. And then close that. Yep. And then we're going to open the function call, and we're going to pass in AD, BD, and CD. And I think we have capital D's in the host code here. Perfect. All right. Okay. And let's give this a whirl. Yay. Look at us. We rule. Right. Okay. Nice work. Okay. Sorry. So one more thing for you here. Okay. So now one thing to think about here, and can you scroll back to the kernel for a second? Sorry. Okay. So we did good. Our arrays match, but believe it or not, we've made an error here. Any ideas what the error we made was here? Yes, I'm hearing that. I'm sure the gentleman in the back said the same thing. We are actually accessing our memory out of bounds here because we've actually launched it with 5 blocks of 512 threads. That's a little early to do, but it's more than 2,500. Now, we only allocated our size to be 2053. So what we're actually going to want to do to make sure that we're not accessing our arrays out of bounds, let's add another argument after the float CD. We'll call it int n. Yeah, and what we'll do with that int n is we'll make sure that our index is less than n before we do the calculation. So between these two lines right there, let's just do an, right there, exactly. We'll do an if index is less than n. Perfect. Exactly. Then we do the addition. So that way we make sure that the threads aren't doing that. Yeah. No, it actually wouldn't have generated an error. Out of range accesses are nasty. It just works, right? If let's say I had allocated another array and it happened to be in that, like, adjacent to that array, it would have overwritten those values, silently. So no, it doesn't. Now in lecture 3 we do debugging. There's some cool things that'll actually let you detect if you're accessing your arrays out of bounds. You can see it says insight there. We'll talk about insight this afternoon in lecture 3 and how it'll actually check, and we'll write out of bounds and it'll pop up a nice warning message for us. But that's just from debugging. But from actual runtime, there's nothing to prevent you from writing anywhere on the GPU. So exactly, we'll have to pass an n there. Perfect. So it should still say arrays match, but now what will happen is that it actually won't be writing out of bounds in this case. So now what we've done in that last block is in that last block of 512 threads, I guess the first 5 of them, or 4 of them, or whatever it is, 6 of them, something like that, will actually do the addition, but the remaining 490 will just do nothing. They won't actually do that operation. So it also shows you can have an if statement in your code. And yeah, there is a bit of a performance implication to doing that, but most of the time, like, you're not going to have nice you're not going to have nice powers of 2 or nice multiples of 512, for example, when you launch your data. So you'll typically have to do something like this to protect the last elements in the array. And that's fine. It turns out, for performance reasons, as long as all your threads in a block branch, and I'm lying because it's a warp, but for now, all in the block branch the same way, there's no penalty for it, as long as you're branching the same way. So only the last block will actually suffer a little bit of a performance hit. And again, we're doing a small number. You're going to be doing tens of thousands of gigabytes worth of data. So it's just at the very end of the array that you're going to suffer that little bit of a penalty. So that's that's the demo. But again, big highlights to kind of remember there's no for loop anymore. This code is being run thousands of times. Oh, sorry, could you just scroll up, Ramesh, for a second? Yeah, it's being run thousands of times by, or 2,053 times specifically, all in parallel on the GPU. So there is no for loop. So great. Hey, Ramesh, thanks so much.
Thank you very much.
Awesome. Yeah, and that brings me to the end of the lecture. I know we're finished about 15 minutes early, but I'm happy to take questions right now, or you guys can come up and chat. If you haven't gotten slides, I think there's still a couple up at the front for this as well. There's probably some scattered throughout if you haven't done that. I also have some contact information. But otherwise, yeah, let's take a bit of a break. I need to put out the next set of slides anyway for the next lecture. And I'm also happy to talk and answer any questions you guys might have as well. So thanks.